Hey, let's go through some briefing before the exam. Chapter 1. The Birth of an Image. Imagine standing at the top of a hill, watching the city below as the sun sets. The sky changes colors orange, pink, then deep blue. You take out your camera, click a picture, and capture that moment forever. But have you ever wondered what happens between the moment you press the shutter button and the moment an image appears on your screen? How does a camera take reality and convert it into pixels, numbers, and colors? This is where the science of image processing begins. At its core, image processing is about taking an image, whether captured by a camera, scanned from paper, or even generated by a computer, and modifying it to improve its quality, extract information, or transform it in ways that reveal new insights. This field combines mathematics, programming, and visual understanding to manipulate digital images. But like any great adventure, our journey begins with a problem. Raw images are rarely perfect. They might be blurry, noisy, too dark, too bright, or simply too large to store efficiently. That's why image processing techniques exist to fix these imperfections, enhance details, and even uncover hidden patterns. Now, Chapter 2. The Miracle of Image Filtering. Imagine you're looking at an old photograph from your childhood. The picture is grainy, with tiny specks of noise covering your face. This is a common problem in digital images. Noise, random variations in pixel values caused by imperfect sensors or environmental factors. The solution? Filtering. Think of an image as a giant grid of pixels, each with a brightness value. Filters are mathematical operations applied to this grid, modifying each pixel based on its surroundings. There are two main types of filters. 1. Smoothing filters. These soften the image, reducing noise and blurriness. 2. Sharpening filters. These enhance edges and fine details, making the image clearer. Now, smoothing filters. The gentle touch. Imagine painting a wall with a roller. The roller spreads the paint smoothly, covering any imperfections. Smoothing filters work the same way by blending nearby pixels to remove noise. Mean filter replaces each pixel with the average of its neighbors, creating a blurry but cleaner image. Median filter sorts neighboring pixel values and picks the middle one, which is great for removing salt and pepper noise. Gaussian filter gives more weight to nearby pixels, creating a soft blur without losing too much detail. Now, sharpening filters, revealing the hidden edges. Imagine drawing an outline around every object in a photo. That's what sharpening filters do. They detect edges and make them stand out. Sobel filter highlights horizontal and vertical edges separately, useful for detecting objects. Laplacian filter finds all edges at once, making images look sharper and more defined. But filtering alone isn't enough. What if your image is not just noisy but also distorted or blurry? This leads us to our next challenge: image restoration. Picture a security camera recording a thief running in the dark. The footage is blurry, making it hard to see the thief's face. Is it possible to undo the blur and restore the image? Yes! This is called image restoration, which focuses on reversing damage and reconstructing the original image. The main techniques used in restoration are: inverse filtering. Imagine a blurry photo caused by motion. Inverse filtering mathematically tries to undo the blur by reversing the distortion. Wiener filtering, a smarter version of inverse filtering that accounts for noise, making it more effective when images are not only blurry but also noisy. Image restoration is widely used in forensics, medical imaging, and space photography, for example. NASA uses it to clean up blurry images from deep space telescopes. Now, the power of transforms. Seeing beyond the visible. What if I told you that every image contains hidden information, details that the human eye cannot see? To reveal these details, we need to step into the world of image transforms. An image is not just a set of colors. It is also a combination of different frequencies. Some parts of an image change slowly, like smooth background areas, low frequencies, while others change quickly, like sharp edges, high frequencies. The Fourier transform is like a machine that transforms an image from the spatial domain, where we see objects, into the frequency domain, where we analyze patterns. Why is this useful? Because once an image is in the frequency domain, we can remove high-frequency noise using low-pass filters, enhance fine details using high-pass filters, and compress images by keeping only important frequency components. But what about compression? That's where the discrete cosine transform DCT comes in, the backbone of JPEG compression. Ever wondered how a JPEG image file is so much smaller than a RAW file? That's because of DCT. It breaks an image into frequency components, removes high-frequency details that the human eye doesn't notice much, and reconstructs the image with fewer details, saving space. But there's an even more flexible approach: the wavelet transform. Unlike Fourier transform, which only works in frequency space, wavelet transform lets us analyze an image at multiple resolutions. This is perfect for denoising images without losing details, compressing images efficiently, like in JPEG 2000, and detecting edges and textures in images. With transforms, we can not only analyze images in new ways, but also improve their quality. But what if an image is too dark or too bright? We need to enhance it. Imagine taking a photo at night. The image looks too dark, with barely any details visible. How do we fix this? That's where histogram equalization, the light balancer, comes in. A histogram shows how many pixels in an image have a certain brightness. If most pixels are too dark or too bright, the image looks bad. Histogram equalization spreads out pixel intensities to create a more balanced, high-contrast image. But if normal equalization over-enhances noise, we use contrast-limited adaptive histogram equalization to make local adjustments instead. Now, imagine you're working with black and white images, but you need to make them easier to understand. This brings us to pseudo-coloring, or painting with meaning. Medical images, like X-rays or weather maps, often need color to highlight important areas. Pseudo-coloring assigns colors based on intensity values, making hidden structures easier to see. With all these tools, we can clean, transform, enhance, and compress images. But there's one final challenge left: storing them efficiently. Images take up a lot of space, and storing and transmitting them requires compression-reducing file size while keeping quality. Lossless compression is perfect for medical and legal images, using techniques like run-length encoding, RLE, and Huffman coding to save space without losing data. On the other hand, lossy compression, used in JPEG, removes unnecessary details to save even more space. That's all I can go through with you. Sorry I can't do more, like with the Python codes or formulas. See you later.